Hi and welcome to my talk on translation certification for smart contracts. My name is Jacco and I'm a second year PhD student at Utrecht University, and this project is a collaboration between Utrecht University and IOG. Right, so IOG is a company that develops the Cardano blockchain, and since it's a blockchain it comes with its own cryptocurrency called ADA. Now, interestingly, this blockchain has support for smart contracts, and that involves a programming language with a compiler. Let me give you just a brief description of what a blockchain is, and for the purposes of this talk, you can think of a blockchain as just a list of transactions, just like it used to be in a traditional ledger. However, this data structure has some specific properties. It is a shared, immutable, and distributed data structure. And what does a transaction look like? Well, it's just something like this. Alice pays Bob a certain amount of ADA. And whenever a new transaction is added to the ledger, the network of the blockchain first has to validate the transaction. And this includes a few checks. First, Alice, of course, has to have the funds to pay, and the transaction has to be cryptographically signed by Alice. Now, when a blockchain supports smart contracts, this allows for an additional entity to be part of these kind of transactions. Specifically, a transaction could look like this, where Alice pays a certain amount into a smart contract. Or later on, a smart contract could pay Bob a certain amount of ADA. And whenever these kind of transactions are validated by the network, an additional check is performed, namely that the conditions of the contract have to be satisfied. A classic example is that of a crowdfunding campaign. So imagine somebody has a great idea, and this person now wants to fund a project. So they set a specific goal. They want to raise a target amount of ADA by a specific deadline. Now, this can be encoded in a smart contract, and whenever that's deployed, participants can contribute to the crowdfunding campaign by paying into the contract. And the contract then has conditions for releasing those funds, which are as follows. The campaign owner can obtain all the funds if the deadline has passed and the target amount has been raised. And otherwise, each participant can reclaim their individual contributions. So what are smart contracts then? Well, they are actually just computer programs, and they are included in the blockchain, which means that once they are committed, the program itself is immutable. And whenever somebody wants to participate in a smart contract, that sort of means that you trust the implementation of that program. Now, obviously, these programs have to be extremely well behaved, and there's a big potential for literally expensive bugs. A famous one is the DAO vulnerability, which was estimated to have cost around $50 million. In the case of the Cardano blockchain, there is the Plutus compiler, and it allows you to write a smart contract in a high-level language of Haskell, which is then compiled down through a few intermediate languages to expressively typed lambda calculus based on system F. And the real question now is, how can I trust such a smart contract? Right, so you could say, well, just give me the source code and I will inspect it, or I might formally verify it. But of course, the real program that runs on-chain is the compiled form of this source code. So what we are looking for here is a verifiable link or a certificate that on the one hand relates the source code to the compiled code, and on the other hand it should formally prove that they have the same behavior, and therefore that the compiler did not introduce any bugs in the smart contract. Our approach to producing these certificates is what we call translation certification. And instead of verifying the whole implementation of a compiler, we consider individual compiler runs. So this technique is known as translation validation. And we consider the compiler to be a composition of individual compiler passes. And the architecture of our certification engine looks as follows. In the leftmost column, you can see the compiler pass, which we denote here as a function fi, transforming one AST in another. And on the right, you can see the certification engine, where we make sure to dump each intermediate abstract syntax tree, and we import that in the certification engine. Here we typically proceed in 3 steps for each compiler pass. The first step is that we characterize the pass as an inductive binary relation, which we call a translation relation. Second, we develop a decision procedure that can relate to subsequently dumped terms. And finally, we prove that the translation relation preserves semantics. Okay, as a first example, I will show how we define a translation relation. And to do that, let's consider the inlining pass. So an inlining pass transforms a program by replacing variables with their definition. For example, suppose we have given this program. Now the inliner can decide to inline the first occurrence of X, and this may reveal opportunities for further optimization passes. In this case, for example, constant folding. Another example would be where each occurrence of X is inlined, and this allows us to remove the definition of X, known as that code elimination, and this is a different optimization. Now in general, it's not always wise to have the compiler inline each occurrence of a variable, because it might be a very expensive computation, and when this happens, you actually you lose sharing and you duplicate work. So the exact variable occurrences that are inlined by a compiler usually depends on subtle heuristics. To model this pass as a translation relation, consider this lambda calculus. It contains variables, lambda abstractions, function application, and in addition, non-recursive lab bindings. We define environments to be lists of lab-bound definitions, and we then define the translation relation as follows. And you should read this as: under environment gamma, an inliner can transform term T1 to T2. We define this relation by induction on T1. So in the case of variables, a variable x may be translated into t when x can be looked up in the environment to be t prime, and t prime can inductively be related to t. Of course, x can also be related to itself, indicating that no inlining has taken place for this occurrence. In the case of lets, a let can be translated into another let if the subterms t1 and t2 can inductively be related. However, in the case of t2, this happens under environment gamma extended with the definition of x. In the case of application and lambda, the rules simply follow by induction on the subterms. It is interesting to note that this relation captures all possible inlining strategies. Now we can encode this relation as an inductive data type in Coq, where each of the data type constructors are one of the rules of the relation. This is a somewhat simple example, but we have used this to model different passes in the Plutus compiler, including dead code elimination, let floating and reordering, data type encodings, and other passes. So in the diagram, this is the definition of Ri, which should be able to relate two terms that were produced by the corresponding inlining compiler pass. Now that we have defined the translation relation, we want to make it decidable. And more precisely, what we're looking for is that when we are given two programs that are dumped before and after the inlining pass, we want to automatically decide whether the translation relation holds. And that means that we need to construct a derivation tree. And we can use different approaches for doing this. The first one is by using Coq's tactics mechanism. And for simple relations like the inliner, we can often find then a derivation by using some of the basic tactics. We also find that this is useful for debugging the design of the translation relation. However, there's a drawback that it's somewhat difficult to reason about the search that's happening here, as the tactics is a form of metaprogramming in Coq. Now, once we have some degree of confidence in the defined relation, we could define a function with the following dependent type, which says, given two program terms t1 and t2, it returns an optional derivation tree of the relation. Now, this might compute large proof terms when succeeding, and it's not always guaranteed to succeed when constructing a proof. So instead, we can also write a proof by reflection, where we define a simple recursive Boolean decision procedure, and then separately we define a soundness proof, which states that whenever the decision procedure returns true, there exists a derivation tree in the relation. And the nice thing is that the only computational part here is a simple Boolean check, a run of the decision procedure. However, proving this reflect property for complex compiler passes is not simple, and we only invest the time when we have a reasonable degree that the relation expresses the compiler pass. So the decision procedure can establish that the translation relation holds for two subsequent programs, and this is indicated by the red line in the diagram. The final step for every compiler pass is then to show that the translation relation preserves semantics. This could be static semantics, where we prove that for any two related programs, that implies that they have the same type. Or, more importantly, we want to prove behavioral equivalence, where we prove that related programs have equivalent runtime behavior. And we built this definition of equivalence on existing work by Amal Ahmed on step-indexed logical relations, which is an appropriate fit for our type system. In the diagram, this semantic preservation proof is shown in the rightmost column. Now, how does all of this fit together? In the end, we're looking to build a certificate as a Coq proof script, which should be generated during the compiler run. It includes the entire set of intermediate programs, all translation relation proofs as obtained by the decision procedures, and finally all equivalence proofs. And by transitivity, we then have an equivalence proof between the source code and the target code. And the idea is to distribute this proof object or proof script together with the compiled code on the blockchain. Now I will say a little bit about the status of the implementation of the certification engine. So when looking at the exact pipeline, we have been focusing mostly on the passes that happen between the intermediate language pair and PLC. And this is where most of the optimizations and interesting desugaring steps happen. So far we have defined most of the translation relations for these passes, and we have some semi-automatic proofs that can relate simple example programs. And finally, we have proven semantic equivalence for one of the passes. One of the advantages that we have found of using this approach is that it's lightweight. And the technique of translation validation means that we don't have to look at the internals of the compiler's implementation. And usually it's much easier to state that a translation is correct after the fact. For example, in the case of that code elimination, the crucial rule in the translation relation looks like this, where we state that a let expression, the binding can be eliminated if the bound variable does not occur in the free variables of the body of the let. Also, the Plutus compiler is developed and maintained by a team at IOG, and they can now largely just do this independently of the certification effort and just focus on compiler engineering instead of proof engineering. Also, the Plutus compiler leverages parts of an existing compiler, GHC, and it is infeasible to do full compiler verification in the style of CompCert, as that would require re-implementing the whole compiler in a proof assistant. Another advantage is what we call gradual development. So when we have defined the translation relations for a compiler pass, we can then separately work on developing the decision procedures and the semantic preservation. And even if we only have a translation relation with a decision procedure, we already have a valuable artifact, namely an independent specification and check that the compiler pass has the right behavior. And we could choose to invest only working on the semantic preservations for particularly difficult, critical, or hard compiler passes. And finally, we find that this certification architecture is robust in the sense that many changes to the compiler don't have to affect the proof infrastructure. For example, if the performance of the compiler is enhanced or the source code is refactored, this is not observable since we're only depending on the intermediate dumped programs. Also, if a compiler pass is changed, for example, the inliner would use different heuristics, this means that the translation relation is completely unaffected and the certifier does not have to be touched. To give you a sense of what this looks like for an actual compilation, here is a very simple example program. It's not too important what it does exactly. It's a trivial smart contract that can lock money until a specific date. But it's programmed in Haskell, and when we run the Plutus compiler, we now obtain all these dumps of the intermediate programs, and we get this as a big const list, and the dumps are annotated with the specific paths that produce the intermediate program. Now let's look at one of those passes, in this case the desugaring of non-recursive lets. So specifically a let in the form of x equals tx in t, it can be desugared into the application of a lambda on the defined term tx. And for the lambda calculus extended with let expressions, the rules can be stated as follows, and this almost directly translates the previous slides into a translation relation where a let is desugared into an application of a lambda and subterms are inductively translated. Now for the actual Plutus ASTs, the implementation is somewhat more involved, but you can still see that there is a rule for lets, and in this case the lets allow for a binding group with multiple binders. But here we just relate such a let expression to a repeated application of lambdas on the bodies of all of these definitions. And then we have two proofs of semantic preservation. Firstly, we prove that this translation relation preserves types, and secondly, we show that any related terms are behaviorally equivalent. Right, so I will say a little bit about what we intend to do in the future. First of all, we would like to develop decision procedures for all of the passes that we have formalized and prove semantic preservation for at least the key passes in the pipeline. Then we'd also like to investigate to scale up vertically and look at the other intermediate languages, such as GCC Core and the surface language of Haskell, which of course are much more involved as they have a larger syntax and a different semantics. And then we're interested in looking into proof transportation, where we would like to take a verification result on the source code, such as some model checker or a theorem that was proven on a specific program, and transport that result over the compiler pipeline to a property on the compiled code. Okay, thanks, and I'm happy to take any questions now.